Hello everyone. Welcome to ILTA Physics Online class. Today, we're going to study various kinds of apparent forces that appear in circular motion. Circular motion involves both real forces and fictitious forces that seem to appear. We're going to take a closer look at these today. First, we'll learn about centrifugal force, which is the force that seems to push an object outward when it's moving in a circle. Then we'll briefly review the apparent forces that we studied earlier in accelerated motion and use that concept to explain apparent weight in circular motion. Finally, we'll talk about the concept of critical speed, the minimum speed needed for an object to maintain circular motion, and wrap up today's lecture. So, shall we start by reviewing what we learned about circular motion last time? Last time, we studied uniform circular motion. Circular motion means motion in which an object moves along a circular path. As you can see in the diagram on the right, for an object to move along a circular path, it must constantly change the direction of its velocity at every moment. This change in direction of motion, more precisely, this continuous change in direction of velocity, is caused by centripetal acceleration, which always points toward the center of the circle. This centripetal acceleration is produced by a centripetal force that acts in the same direction. To summarize again, for an object to move in a circle, there must always be a centripetal force acting toward the center of the circle. This centripetal force produces the centripetal acceleration, and that acceleration changes the direction of the velocity. Therefore, the object moves along a circular path. The velocity of an object in circular motion is always tangent to the circle, and the centripetal acceleration is always perpendicular to that velocity, pointing toward the center. We can express this relationship mathematically as follows. Centripetal acceleration can be calculated as the square of the velocity divided by the radius. The relationship between the force acting on the object, its velocity, and its acceleration in circular motion can be explained using Newton's second law of motion, F equals ma. What this equation means is that the centripetal force required for circular motion is equal to the net force acting on the object, that is, the vector sum of all forces, and that this net force equals the mass of the object multiplied by the centripetal acceleration. Since we are dealing with circular motion, the acceleration term in Newton's second law is replaced with centripetal acceleration, as shown in the equation. We also looked at this kind of motion from the perspective of periodic motion. In circular motion, the period is defined as the time it takes for the object to make one complete revolution around the circle, and the frequency is defined as how many revolutions the object makes per second. Therefore, the period and frequency are reciprocals of each other. Using the period and frequency, we can calculate the speed of circular motion. The speed equals the circumference of the circle divided by the period, and it can also be expressed in terms of frequency. Then, using the definition of centripetal acceleration, if we substitute the expression for speed, we can derive the following equation. It's better to understand these equations rather than just memorize them. Now, using these basic relationships of circular motion, let's move on and explore the apparent forces that appear in circular motion. The first apparent force we're going to look at is centrifugal force. Centrifugal force refers to the feeling of being pushed outward when an object is moving in a circle. For example, imagine you're in a car that's driving around a curved track, like in the picture on the right. When the car turns a corner at a certain speed, have you ever felt your body being pushed outward toward the outside of the curve? That force you feel is what we call centrifugal force. However, this centrifugal force does not actually affect the motion of the object itself. It's a force that appears because of the object's inertia, but from the point of view of the object's actual motion, it's not a force we need to consider. To fully explain centrifugal force physically, we'd need to go into a bit more depth, but for now, let's keep it simple and think about it this way. As shown in the picture on the right, imagine a car turning around a curved corner. We usually describe the motion of a moving object from the outside. For example, as if we were watching the car from above, describing its direction, speed, and distance. This is what we call an inertial frame of reference, which is the kind of system Newton's laws of motion apply to. However, a person sitting inside the car thinks of themselves as being at rest. In other words, just sitting still in their seat while describing what's happening. For that person, the outward force they feel, shown as a circle in the picture on the right, is what we call the centrifugal force. This situation is an example of a non-inertial reference frame. You can probably already guess that these 2 points of view, the outside observer and the observer inside the car, are quite different, right? The centrifugal force is a force that the passenger feels while moving with the car, so it doesn't actually affect the car's motion itself. We'll talk more about the physical laws that apply to non-inertial frames later on. Therefore, the centrifugal force is not shown in a free body diagram, and Newton's laws of motion do not apply to it. Finally, because the centrifugal force acts in the exact opposite direction of the centripetal force, it's easy to mistakenly think that the two are an action-reaction pair. Centripetal and centrifugal forces are not action-reaction pairs because they act on the same object, not on two different objects. So in conclusion, at our current level, we can summarize it like this. The centrifugal force exists only in a non-inertial frame of reference. But since it doesn't actually affect the motion of the object, we don't need to consider it when analyzing motion. Now, another kind of force that appears in circular motion is apparent weight. Let's take a moment to quickly review the concept of apparent weight we studied earlier in uniform accelerated motion before moving on. First, remember that weight is the force of Earth's gravity pulling on an object. It's different from the object's own property of mass, but since the acceleration due to gravity is constant here on Earth, your weight always has the same magnitude. On the other hand, apparent weight is the force you actually feel as your weight. Your sensation of weight, how heavy you feel, is caused by the contact forces that support you. For example, when you're standing on the floor, that contact force is the normal force. And when you're hanging from a rope, it's the frictional force in the rope. But here's what's really important. Your apparent weight can change depending on the motion of the object you're in. Remember the diagram on the right? The weight that a person feels while standing in an elevator is an example of apparent weight during linear accelerated motion. So, what kind of force represents the apparent weight in this case? Yes, it's the normal force from the elevator floor pushing upward on you. That upward push from the floor is exactly what you feel as your apparent weight. We need to make sure we understand this clearly before moving on. Now, since apparent weight can change depending on motion, let's look at a few different cases. First, if the object is in equilibrium, that means it's either at rest or moving at constant velocity, then your apparent weight is equal to your actual weight. In the diagram above, when the elevator is at rest, the downward force of gravity, your weight, W, pulling you down, is exactly balanced by the upward normal force, N, from the floor pushing you up. So in that case, your apparent weight equals your true weight. Now let's think about the case where the elevator is accelerating upward. That's the situation shown on the left in the diagram. If you draw an accurate free body diagram and apply Newton's second law, you'll get the relationship shown below. But let's also think about it intuitively. When you're at rest, your weight and the normal force are balanced, equal in size, opposite in direction. However, if an external force pulls the elevator upward, these upward forces add together. So the total upward force becomes larger. That means the elevator floor pushes up on you with a stronger force, so you feel heavier. Your apparent weight is greater than your actual weight. Mathematically, we can say your apparent weight increases in proportion to the upward acceleration. On the other hand, if the elevator accelerates downward, the external force acts downward, which partially cancels out the upward normal force from the floor. As a result, the total upward force becomes smaller, so your apparent weight feels lighter than your actual weight by an amount proportional to the acceleration. The concept of apparent weight in circular motion, which we'll study on the next slide, can be understood in a similar way. And finally, in a third situation, if the elevator keeps accelerating downward faster and faster, your apparent weight will keep decreasing. At a certain point, your apparent weight becomes zero. This is the weightless condition, or zero gravity, which is what an object experiences when it's in free fall. Today, we're going to apply this concept of apparent weight to the case of circular motion. Now, let's think about apparent weight in circular motion. The picture below shows a diagram of a roller coaster standing on a vertical loop. Imagine a roller coaster car coming in from the left, going all the way around the loop once, and then exiting to the right. Sounds fun, right? When the roller coaster car moves through the loop in circular motion, there are two critical points you should remember. First, since the roller coaster is in circular motion, there must be a centripetal force acting toward the center of the circle. And second, the apparent weight that you feel while sitting in the roller coaster car is the normal force of the seat pushing against you, supporting your body upward. To correctly apply these two facts to the concept of apparent weight in circular motion, you need to understand and use the following two key ideas. First, earlier we said that circular motion requires centripetal force. Let me emphasize once again, many people misunderstand this and think that circular motion itself somehow creates a centripetal force, but it's actually the opposite. There must first be a centripetal force directed toward the center of the circle. That force produces the centripetal acceleration, and that acceleration changes the direction of velocity, which is what creates circular motion. Make sure you understand this cause and effect relationship clearly. And second, the apparent weight you feel while sitting in the roller coaster car is the normal force that the seat exerts on you to support your body. Now, what direction should that normal force point when the roller coaster car is at the top of the loop? At that point, the seat actually pushes you downward. In other words, the normal force points downward at the top of the loop. Keeping these two facts in mind, let's draw a free body diagram for the roller coaster in different positions in the next slide. First, let's consider the roller coaster when it's at the bottom of the loop. Because the roller coaster car must maintain circular motion, there must be a centripetal force acting upward toward the center of the circle. And the weight always acts downward. Now, let's think about the normal force that provides the centripetal force needed to keep the object moving in a circle. The normal force from the seat must be large enough to balance the downward weight and still provide the extra force needed for the centripetal acceleration. To say it another way, for the roller coaster car to move in a circle, an upward centripetal force, shown by the red arrow, is required. But since the weight of the car, shown by the gray arrow, acts downward, the normal force, shown by the blue arrow, must be stronger than the weight to make up the difference. And that normal force is exactly what you feel as your apparent weight when the roller coaster car is at the bottom of the loop. In other words, you feel heavier than your actual weight. Now, can you see how this situation is a little different from the elevator example we studied earlier? In the elevator case, there was an external force pulling the elevator upward or downward, So we analyzed apparent weight as a change in balance due to that external force. In the roller coaster case, however, there's no external pulling force. Instead, the normal force must adjust its strength, increasing or decreasing, to provide the required centripetal force for circular motion. Make sure you clearly understand and compare these two situations. Now, let's draw the free body diagram when the roller coaster is at the top of the loop. At the top, in order to maintain circular motion, a centripetal force, represented by the red arrow, must act downward. The weight of the roller coaster car always acts downward as well, shown by the gray arrow. So to create the required total downward centripetal force, the normal force only needs to be a smaller downward force, represented by the blue arrow. Since the normal force from the seat pushing downward on you is what you feel is your apparent weight at the top of the loop feels lighter than your actual weight. Be sure to review this explanation several times until you fully understand it. Now, let's move on to calculate the apparent weight quantitatively using Newton's second law, based on the ideas we've just discussed qualitatively. Earlier, we drew the free body diagrams for the roller coaster problem. Now, let's apply those diagrams and Newton's second law, the law of acceleration, to quantitatively calculate the apparent weight. First, let's look at the case when the roller coaster is at the bottom of the loop. All the forces act in the vertical direction, that is, along the y-axis. So, their total must provide exactly the centripetal force needed to keep the roller coaster moving in a circle. That centripetal force is the net force we are trying to find. In the free body diagram, let's define the positive direction of motion as the upward direction, the positive y-axis. Then the net force, that is, the force required for circular motion, can be expressed as the upward normal force minus the downward weight. Since this net force produces the object's acceleration, in this case, the centripetal acceleration, we can write the relationship using the equation F equals ma. Be careful with the signs in the equation, depending on the direction of the normal force and the weight. Because we said the normal force, the seat pushing on you, represents your apparent weight, we can rearrange the equation to show that your apparent weight is greater than your actual weight by an amount equal to the centripetal force. So mathematically, you feel heavier by exactly that amount. Now, let's do the same kind of calculation for when the roller coaster is at the top of the loop. Again, to maintain circular motion, a centripetal force is required toward the center, which in this case means downward. As we explained before, remember that the normal force, your apparent weight, at the top also points downward. Since your weight is already acting downward, only a small additional normal force is needed to produce the total centripetal force. If we express this situation in an equation, all forces point downward, so they'll all have negative signs when written in terms of direction. The net force is again equal to ma, which gives the required centripetal force. When we solve for the normal force, we find that the apparent weight comes out smaller than your actual weight. Finally, let's briefly talk about the critical speed. The critical speed is defined as the minimum speed required for an object to maintain circular motion. In the case of the roller coaster, when the car reaches the top of the loop, if its speed is too slow, it won't have enough centripetal force to stay on the track, and it would simply fall straight down in free fall. That would cause a serious accident, something that must never happen. To avoid this situation, the roller coaster needs to maintain at least the minimum centripetal force required to stay in circular motion. This condition occurs when the normal force, that is, the apparent weight, becomes zero. When the normal force is zero, the only force providing centripetal acceleration is gravity itself. That's the situation that defines the slowest possible speed for circular motion, the critical speed. You can think of this as being very similar to the weightless condition we talked about earlier during free fall. We'll study the concept of critical speed in more detail and with more precision later when we talk about orbital motion. That's all for today's lecture. Great work, everyone. I'll see you next time.